Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of the operating system lectures, we were discussing about this synchronization problems. We have seen several solutions to the synchronization problem, and in today's lecture we will discuss about the semaphores and its types. So, the outline of the lecture would be that we will first have the recap of the cooperating and the competing processes, and then we shall see what are the solutions with the busy waiting. We have also discussed the solution with the without busy waiting. So, we shall see that as well, and finally, we will have a discussion on the semaphores, the counting semaphore and the binary semaphore. So, we have seen that in the previous lectures that there can be two types of the processes, the cooperating processes and the competing processes. The meaning of the competing process is that where there is a race between the processes to have the access to the common resource, and the cooperating means a process produces an item and the other process consumes that, or there is a cooperation maintained in between the processes to access to those resources. This can be in the form of the shared variable, or this can also be in the form of the shared region of the memory that can have the access by the different processes. So, the cooperating process is one that can affect or be affected by other processes executing in the system. Cooperating processes can either directly share a logical address space, that is both data in the code, and but this is done through the threads. Threads can run in parallel, or be allowed to share the data only through the files and the messages, and this is actually done with the help of the synchronization mechanisms. The concurrent access to the shared data may result in the data inconsistency. The final value of the data may get different from what we expect it to be, and we have discussed various solutions to this synchronization problem. We have also seen that whenever there is access to the common resource or the shared resource, or a piece or part of the code where we are using the shared variable or the shared resource, we say that that portion of the code is the portion of the code is called the critical section. Now, critical section means the part of the piece or part of the piece of the code where we are using the shared variable. We can use the shared variable multiple times in the same program or same code. So, hence we can have several critical sections in our program. Any other code written in the program is known as the non-critical section. So, a part of the code where the shared memory is used, we call that a critical section, and solution to the critical section problem is known as the synchronization, and we will see that how the synchronization will be achieved, or we already have seen how the synchronization are getting achieved with the various schemes in the previous lectures. Now, whenever we are dealing with the critical section and we have to find out the solution to the critical section problem, the piece of the code is actually sandwiched in between the entry and the exit section. So, the entry section is a part of the code that applies some conditions before entering into the critical section, or some conditions are checked in the entry conditions while entering in the critical section or while having an access to the critical section. So, the piece of the code is applied here, some conditions are applied, some variables are set, some values are set, and while exiting the critical section, the exit section code is executed, and those conditions which were applied in the entry conditions or entry section will be removed. For an example, if you are taking a lock variable, if the lock value is set to 0, it means the entry to the critical section is allowed, but before entering in the critical sections, the lock is set as 1. So, lock is set by 1 in the entry section, and the critical section executions takes place, and after that, when critical section execution completes, the exit section sets the value of lock again as 0, such that the other process which wants to enter the critical section may have the access of the lock variable as 0. Now, we have seen several solutions for achieving the synchronization. So, we have seen various solutions on the last turn. We have seen the use of the lock variable for setting up the entry in the critical section. And when we are using the lock variable, we were first checking whether the value of lock is 0 or not, and then we will have to check if the entry can be allowed if the lock is 0. So, while entering to the critical section, we will set this lock as 1. So, when we expand this can be expanded into few statements, let us say 4 statements, and if these 4 statements are executing at the same time, it is not possible the preemption can take place in between. So, if the preemptions are allowed, the very purpose of achieving the mutual exclusion cannot be achieved here. So, the lock variables, yes, it is not able to provide the mutual exclusion in case the preemption is allowed in between. If we expand this code and we allow the statement to be like this, let us say moving the content of the lock in, let us say, some R0 register, and then setting up value 1 in the lock. In case the preemption is allowed in between these two statements, we cannot achieve the mutual exclusion. Now, since mutual exclusion cannot be achieved, let us try to run these two statements in parallel. So, if the not in the parallel, it means one after the other, but it should be unified in one statement or in one unit. So, it cannot be a software solution if you are allowing these two statements to run at the same time or in one unit. So, this has to be the hardware solution. So, hardware solution can be achieved with the help of the combining these two statements or fabricating these two statements in some chip, but at the same time the solution that we are building may not be architecturally neutral. So, there is a problem of the architectural neutrality here in this solution, and we call this a use of test set lock, the TSL. So, the another approach is use of the strict alteration approach, wherein we can make use of the turn variable, and which the turn variable is initialized to 0. When the value of turn is 0, it means the process number 0 can enter the critical section, and while exiting it makes turns to 1, it means the process number 1 can enter the critical section, and then process number 1 enters the critical section, it executes the critical section, and after exiting it sets the value of turn as 0. So, there is process 0 executes, then process 1 executes, then again process 0 executes, then process 1 executes. So, alteration is there, so bounded wait will be there. Now, the progress, what about the progress? If P0 process is entering the critical section and after the exiting it sets turns as 1, it means that the process 1 can enter, but process 1 is not interested. So, if process 1 is not interested, it means that the process number 1 is neither executing the critical section nor it is going to allow other process to enter to the critical section. So, there is a problem with this. So, progress property is not satisfied in this case. So, let us use the interest variable. If a process is interested in entering to the critical section, it will check the code. If it is not, it will not check the code. So, interest variable will be set by these processes while entering into the critical section, but this problem suffers with the deadlock problem. So, the best solution among all these is the Peterson solution, and the Peterson solution says that make use of the turn and interest both. So, if it is making use of the turn, it means progress is satisfied, bounded wait is satisfied. If it is making use of the interest, it means the progress is satisfied. So, progress and bounded wait both are satisfied, and since this solution is the software solution, it is not architectural, it is architectural neutral. So, this solution satisfies all 4 conditions which are required to be satisfied by the synchronization mechanism. But there is a problem with these approaches. These approaches are not allowing the CPU to get into rest. The CPU is continuously checking these statements. This is a busy waiting solution. So, we are keeping CPU waiting all the time or CPU busy all the time. So, these solutions are not supposed to be the good ones, because CPU is unnecessarily kept busy. So, let us discuss a solution which is not a busy waiting solution. This is without busy waiting solution. On the last time we have seen the example of the bounded buffer, and the bounded buffer problem, in the bounded buffer problem the consumer problem was sending or consumer problem was sent to sleep and it was waking up the producer problem. Similarly, the producer problem was going to sleep and it was actually waking up the consumer process. So, one process will be waking up the other process will be waking up the other process. So, a process goes to sleep when there is nothing, no work is pending, or when there is no operations possible. Why to keep the CPU busy unnecessarily? So, we have discussed about a semaphore solution also, and we have seen that the semaphore is a shared variable, and this is a shared variable that can be accessed in the kernel mode only by the defined process. So, there are two processes that we have discussed. One was the wait and another one was the signal. You can say that these are not the process, but these are the functions. So, these functions have the access to the semaphore. Whenever you have to enter to the critical section, you will check the wait condition, or you will apply the wait condition, or you will actually execute this function. This function will make certain changes to the semaphore value, and while exiting the critical section, we will actually up the signal value to by 1, such that the other process can enter into the critical section. So, the semaphore value can be accessed through the binary through the wait and the signal function only. Now, these semaphore values can be of two types. One is the binary semaphore and another one is the counting semaphore. If the value of the semaphore is 1 or 0 only, it can either be 1 or 0, then we will say that we are dealing with the binary semaphore. If the value of the semaphore varies from some n and it can go to any number, then we will say that this is a counting semaphore. We have taken an example of the printer. Let us say there are 4 printers available in the system. So, obviously, we can initialize the semaphore value to 4. Okay? So, it can be 4, then 3, then 2, then 1 and then 0. So, semaphore value can be 4, 3, 2, 1 or 0 in case we are not allowing the busy waiting, but if we are allowing the busy in case we are allowing the busy waiting. In case we are allowing the busy waiting also non busy waiting, we are going to put some process to go to sleep and then we will wake it up, then the value of the semaphore will be reducing to -1, -2, -3 also upon executing the wait functions several times. We will see this with an example, do not get confused in case you are here. Now, these are the two functions, the wait function and the signal functions. These are the basic functions to be used with the binary or the counting semaphores, and this is the busy waiting solution. In the busy waiting solution of with the semaphore, what is said that the semaphore value, which is initially at 1, if its value goes down to 0 or it is less than 0, the entry to the critical section will not be allowed and we will keep checking it. So, there is a busy waiting. So, if the value of semaphore is 1, we can enter in the critical section, but before entering to the critical section, let us reduce the value of semaphore from 1 to 0, so that other process cannot enter into the critical section. Now, when you have executed the critical section, you should allow the other process also to get into the critical section. So, while exiting the critical section, the signal function is called and the signal function increments the value of the semaphore from 0 to 1. So, this is the simple technique by which the semaphore values can be accessed through the wait and the signal. In the entry section, we will apply the wait. In the exit section, we will apply the signal. Now, let us say we are dealing with a counting semaphore. We will discuss about the binary semaphore also. Let us say we are dealing with the counting semaphore and we are not allowing the busy waiting. Let us do it with the without busy waiting solution. So, let us say the value of the semaphore is initialized to 3. It means the 3 processes can enter in the critical section at the same time. It means that there are, let us say, 3 printers and 3 processes can have the access to those printers. So, let us say a process P0 comes and process P0 executes wait. So, if process P0 applies the wait, the value of semaphore goes down from 3 to 2. Obviously, in the wait function, we will decrement the value of semaphore. Now, P1 process comes and the wait function reduces its value or the value of the semaphore from 2 to 1. Now, here it is interesting to see that the process number 0, after having found the value of semaphore positive, will enter in the critical section. Similarly, the process number P1 will enter in the critical section upon seeing the value of semaphore as positive, and then the P2 process executes the wait and it also sees the value of the semaphore as positive. So, it makes the value of semaphore from 1 to 0 and enters the critical section. Now, after this the P3 process comes and P3 process sees the value of semaphore not positive, it is the 0. So, it will reduce the value of semaphore from 0 to -1 and will go and sleep. Okay. We are maintaining some, let us say q, and the P3 process will go and sleep. Similarly, P4 process also wants to enter to the critical section. So, it sees that the value of the semaphore is -1, it is not positive. So, it makes the value of the semaphore as -2 and P4 process goes to sleep. So, here in this case what is happening, that semaphore value was initialized to 3, it means 3 process can enter in the critical section. P0, P1, P2 process are in the critical section, and 2 more processes are interested in entering into the critical section, but they cannot be allowed at the moment. So, these 2 processes P3 and P4 will go and sleep. Okay. Now, if the value of semaphore is 4, it means that 4 processes can enter in the critical section. Fine. Now, let us say the value of semaphore is 3, let us demonstrate it once again what we have discussed, and let us see what happens if one of the process exits the critical section. So, here this we have already seen that the P0, P1 and P2 process are in the critical section, but P3, P4 processes are in the waiting state. So, let us say these are in the queue. Now, in the queue we have P3 and the P4 process. Let us say P0 process exits the critical section. When P0 process exits the critical section, then it updates the value of semaphore from -2 to -1 by the signal function. It executes the signal function and the value of semaphore goes up to -1 from -2. The value is value is still negative. So, a process will be taken out from the here and P3 process enters the critical section. Okay. So, one process P3 from Q is taken up and will enter the critical section. So, this P0 exits and P3 will enter the critical section. Now, after this let us say P1 also exits. If P1 exits, it executes the signal function. If it executes the critical section, the value of the semaphore goes down to 0. It is still not positive. So, since it is not positive, one process from the queue will be taken up and it will be allowed to enter to the critical section. So, this P4 process enters the critical section. Okay. Let us say one more process exits the critical section, let us say P2. So, the value of this goes from 0 to 1, the value of the semaphore goes to 1 from 0. So, this becomes positive. Meaning of the positive is that there is no process in the queue. So, do not allow any process to enter the critical section anymore. So, this goes like this. So, we are actually implementing the counting semaphore here, and what happens in the case of the counting semaphore, that a semaphore is initialized with its value and a queue also, because we are maintaining a queue for putting the processes which are going to sleep. Now, the down semaphore decrements the value of semaphore, and after this if it checks that if the value is less than 0, it means that we have to put this process in the queue in the sleeping mode. Otherwise, just finish this and enter in the critical section. Now, the up semaphore, or what is down and up, the down is said to be wait and the up is said to be the signal. Down and up is same as wait and signal. So, it increments the value, the signal or up increments the value of the semaphore. If the value is less than or equal to 0, it means some process are waiting in the queue. So, let us take a process, select the process from the queue and wake it up and enter into the critical section, or allow it to enter into the critical section. We have already seen this with this example. So, this is actually the counting semaphore. So, what is the counting semaphore? The order in which the process are blocked. Obviously, P3 was blocked first and then P4 was blocked. So, when we were resuming them, P3 was unblocked first and then the P4. So, bounded wait is satisfied here, and we are obviously allowing one process to enter into the critical section at the same at one time. So, mutual exclusion is guaranteed. Fine. So, progress is also guaranteed, because if a process has to enter into the critical section, it will run the wait process. If it does not have to enter to the critical section, it will not run the wait process. So, we already have shown that the down is same as wait, it is also known as P, a very famous name for this decrement, this is P, and then up is same as the signal, this is a famous name known as V. So, P and V are the functions that we should be using here. Now, this is the problem, let us solve this problem. A counting semaphore was initialized to 10, 6 P operation and 4 V operations were carried out on the semaphore. So, what is the result? So, obviously, with the help of the P operation we are decrementing the value. So, we will be decrementing 6 times the value of the semaphore. So, 10 to 9, 9 to 8, 8 to 7, 7 to 6, 6 to 5 and then 5 to 4. So, this is the 6 times, and then 4 V signal operations were carried out, V or signal operation. So, in the signal operation we increment the value of semaphore. So, 4 to 5, 5 to 6, 6 to 7 and then finally 7 to 8. So, the final value of the semaphore is 8. We can also do it like 10 is the initial value, 6 P operations were carried out and 4 V operations were carried out. So, this is 10 minus 2, that is equals to 8. So, this is the final value of the semaphore. Let us take another example. What this is saying that the semaphore value was initialized to 7 and 20 P operations and 15 V operations were carried out. So, what is the final value of the semaphore and how many processes are there in the critical section, how many processes are there in the queue. So, it is very interesting to see that the value of this is initialized to 7, but we are doing it 20 times. The P operation or the wait operation is carried out 20 times. So, with the help of the wait operation the value of semaphore will reduce to 7 minus 20 means minus 13, and after this the 15 V operations are carried out, it means the value of the semaphore will be going to 2 from minus 13. Okay. Now, you can see that the question is asked what is the final value of the semaphore, obviously it is 2. Okay. The initial value of semaphore was 7, it must have gone from 7 to 6 to 5, 4 and 3 then 2. So, 1, 2, 3, 4, 5 processes will be there in the critical section at this moment, and how many processes were there in the waiting queue, how many processes are there in the waiting queue. Okay. So, it is asked that how many processes are there in the waiting queue. So, the semaphore value is positive at the moment, how can any process will be there in the critical in the waiting queue. But if we want to find out how many maximum processes were there in the queue, so that can be found by 7 minus 20, this is minus 13. So, there will be 13 processes in the queue maximum at any moment. Okay. We can solve several problems also related to this, but now let us see the binary semaphore, which says that the value of the semaphore can only be 1 or 0. So, the value of binary semaphore can be only 1 or 0. So, maintain a queue also, we are doing the without busy waiting solution. The binary semaphore says that if the value of semaphore is 1, the entry to the critical section can be allowed, so make it 0, but if it is not 1, then put the process to sleep. When we are executing the signal operation or the up operation, if the queue is empty, set the value of binary semaphore as 1, otherwise if queue is not empty, put a process or take a process from the buffer and wake it up for the execution. Okay. So, this is the binary semaphore. This is the reference for this lecture, and we have seen that binary semaphore and the counting semaphore are providing the desirable solution, and these down and the up operations are running in the kernel mode. There are many more things that you can learn from this book, the book of Silberschlag and Galvin. This is one of the best books of the operating system. All the concepts related to the synchronization cannot be discussed in the class. There are several problems which come in the gate examinations, you should also go through them. Thank you.